Hello everyone, myself Dr. Naresh Sarkar and I welcome you all in the lecture series of nanomaterial synthesis and its characterization. Today I will going to discuss about how to determine the crystal structure from the data which is coming from the XRD machine. So this topic is determination of crystal structure by indexing method. Friends, let's discuss with an example of body-centered cubic. When you synthesize your material in a lab, your material may be crystalline in nature or may be amorphous in nature. If your material is crystalline in nature, then it should be matched with 7 crystal system out of the 14 Bravais lattice. If your material is crystalline in nature, then this crystal may arrange the atom is periodically, and the planes where you count the atom and the atomic density is different for the different planes. So here I will going to discuss when the X-ray beam which is coming from the X-ray source, then the angle of incident and angle of scattered for the different atomic density or different plane is different. Suppose here with an example of body centered cubic, that body centered cubic having the plane 110. So this is 110 plane. So if it is a 110 plane, so I will take the reciprocal of this 110 plane. That means that 1 is divided by 1 and this 1 is divided by 1 and the 0 is also 1 divided by 0. So 1 divided by 0, it is infinite. That means this HKL plane indicating the point of x-axis, y-axis and z-axis. So here it is for z-axis it is infinite, so we don't know at what point it is cut. So that is why at x-axis it is cut at point x, and for the y-axis it is cut at point the 1. So that means if from it is the origin O, and from this origin O if it is a point 1, so here it is 1 cut by this plane, and for the y-axis if it is origin O and up to this unit point, say it is a 1, so the plane which is cut from here to here, but we don't know this plane is cut where in the z-axis. So this body centered cubic having the n number of HKL planes of 110. So this is one unit cell, and using this corner atom there is a one more unit cell, that unit cell having the same HKL plane with this atomic density of direction. So these two planes are parallel to each other. So likewise n numbers of plane in a crystals which are parallel to each other, and these three planes or material when I am put in a crystal in a XRD machine, and when the X-ray beam are scattered, then with this atom they are reflected with this atomic arrangement and they are recorded. This beam is recorded, or scattered or reflected beam is recorded by the detector only when they are produce a coherently and constructive interference pattern, and they are constructive interference pattern produced only when they satisfy the Bragg's condition. Okay, that Bragg's condition is 2d sin theta is equal to n lambda. When they satisfy this condition, then and only they produce a constructive interference pattern, and once they produce a constructive interference pattern with these two waves, then they are recorded with the reinforcement of this two wave, and that time they are recorded by the machine, and that is called this peak recorded at this point theta. So here the angle of incident and angle of scattered play a very important role, because only that particular angle 20.01 degree they satisfy the Bragg's condition and produce a constructive interference pattern, and therefore the beam is recorded. So this is 20.1 degree. What if I change this angle with 20.1 to some other angle, or incident angle or a scattered angle? So they could not follow the Bragg's condition. Suppose here it is 20.1 degree and they are follow the constructive interference pattern. Now if I change this angle of incident, then the scattered angle also get changed. So that time they are not satisfied the Bragg's equation. So the destructive interference pattern is produced. So here it is not following the Bragg's condition. So the destructive interference out of the phase, so no peak is recorded. Okay, so likewise, if we change the angle in the different atomic density, then it may be either follow the Bragg's condition, either may not be follow the Bragg's condition. If it is follow the Bragg's condition, then it is recorded the peak, otherwise not. Let us see of the BCC structure with the different plane. Here it is the material is same, but the atomic density or the plane is different. This 200 plane having the different atomic density as compared to 100 plane. So if you take the reciprocal of this 200 plane, so it will get 1 by 2 infinite and infinite. For the x-axis it is 1 by 2. Here suppose it is to be cut, and z-axis we don't know, and y-axis we don't know where it is cut. So it is doesn't cut at z-axis and y-axis. It is only cut at the x-axis up to from 0 to origin to half point only. So this HKL plane in the BCC structures have n number of HKL planes of 200. So this is for one unit cell. Likewise, there is a one more unit cell, n number of unit cell in this crystal. So this crystal in a n number, this HKL plane in these crystals are parallel to each other. Suppose this is one plane, this is another plane. So likewise, all the 200 planes which are parallel in this crystal structure, and when we put this material, this type of material in X-ray XRD machine, likewise, so this is the different atomic density arrangement. So if we put this material in XRD machine and we apply the incident X-ray, then it is again reflected by this atom, and detector is detected only when they follow the Bragg's condition. Okay, so here it is the different angle with this different plane. So this angle is recorded because it is a constructive interference pattern, and this angle is supposed to be here. It is 29 point something. This is 29.1. So see, the atomic density is different with the different atomic plane. 2001 plane, the angle of incident is different. So for 100 plane, the angle is 20.01. Then only they satisfy the Bragg's equation. Here angle is 29.1 for this 200 plane. Then only they satisfy the Bragg's condition and recorded the theta value. So likewise, when this equation and this angle of incident are matched with each other, likewise they recorded this type of X-ray diffraction pattern. They recorded this type of X-ray diffraction pattern here. So if you observe it carefully, this is the 2 theta position in x-axis, and this is the intensity count, and this theta is 20.1 for this 100 plane, but it is actually a 2 theta. So double of this 2 theta is 40.2. This is 40.23. Here it is recorded for this BCC structure, and this is the plane indicating 110, and this is the fingerprint of this material at a certain particular angle, 40.2031 of the 2 theta. Then this plane is 110 plane, and this is 29.1 for the theta. So double it because it is a 2 theta, so it is 58.22. So it is the plane 200 plane, and intensity is also depends on the atomic density and atomic position also, that I already discussed in the previous lecture. So this is the fingerprint of your material when they are reflected at particular theta angle with a particular plane. So let's understand with the one more example and indexing this 110 plane, because how to indexing this 110 plane, that we will index in the next slide, and we will find out the lattice parameter and HKL values of the data which is coming from the machine. Friends, in this slide I am going to show the D value or D spacing value for the different crystal system. Here it is the cubic crystal system, tetragonal, hexagonal, rhombohedral and orthorhombic. So the cubic system having the different formula for calculating the d value. Here it is 1 by d square is equal to h square plus k square plus l square, and this whole divided by a square, where a is the lattice. This formula is different for the different crystal structure, so I will show how to use this formula for indexing the HKL value or find out the lattice parameter using the XRD data. So here it is the new form of Bragg's equation. You know Bragg's equation is 2d sine theta is equal to n lambda. So that means 1 by d is equal to twice sine theta by lambda. So which is also you can write by squaring this equation. 1 by d square is equal to 4 sine square theta by lambda. But we know using this cubic system, because I am going to show an example of cubic system. So here we know 1 by d square is equal to h square plus k square plus l square, and this is whole divided by a square. By interchanging this equation or rearranged with this Bragg's equation, we can find out if it is 1 by d square. If I put this value of left hand side to this equation, so I can get this h square k square plus l square by a square is equal to 4 sine square theta by lambda. So likewise, if you rearrange this equation, you find finally this equation sine square theta is equal to lambda squared by 4 a square, and which is multiplied by the Miller indices HKL plane. So where lambda and a are constant, because lambda we are taking fixed 1.54 angstrom unit for the CuKL for radiation, and a is lattice constant, which is also fixed for the any atom. So this lambda and a and 4, these are the constant factor. That means this sine square theta is proportional to the h square plus k square and l square value, because theta is variable in 2 theta position and intensity count in the XRD pattern. So using this relation, we're going to solve the data which is coming from the machine. So one thing you should keep it in mind, for the simple cubic, the first reflection which is coming from the XRD machine, the first reflection or first plane for the minimum theta, that is 100. For the body centered cubic, 110, and for the face centered cubic, it is 111. Okay, so for simple cubic, h square, k square and l square value must be 1 for the first reflection or in the minimum lowest theta value, and for the body center, this summation of this h square, k square, l square is must be 2, and for the face center is must be 3, and this is for the first reflection. Keep it in mind, please. So these are the conditions for the allowed reflection cubic. First is the primitive, the all possible HKL values are allowed, and for the body centered, so friend, you should, this is the very important point I am going to discuss here. The reflection is allowed only when for the body centered. If your crystal is a body centered, then the h square plus k square plus l square value is must be even. Suppose 2 2 0, then this 2 square plus 2 square is equal to 4 plus 4 8. So if it is 8, means it is the even number, then it is allowed. If it is 7, like 2 and 1 2 1 0, then 2 means 2 square for h, this is 4, then plus 1, so it will be 5. So it is odd. So if it is odd, means summation of this h square plus k square plus l square, if it is odd, then it is not allowed in the body centered. But in the case of face centered, the reflection is allowed only when the value of h, k, l are either even or either odd, but not even and odd value. Suppose for example 3 1 1 is the HKL plane. 3 is a odd number, 1 is a odd number, and 1 is also a odd number. So that is why it is either even either odd. So this 3 1 1 peaks or planes are allowed, but 2 1 0 is not allowed, but 2 2 2 it is allowed, because all HKL are the even. So keep it in mind, please. If it is a even all HKL values, then also allowed, but if it is a odd, then also allowed, but it should not be mixed with even and odd value. So using these combinations or this technique, I can mention here for the primitive, if your crystal system is a primitive, then there is a 1 2 3 4 5, all reflections are allowed. These are the sequence, If it is a body center, then the value of this HKL must be 2, 4, 6, 8, because it is all are even, 2, 4, 6, 8, 10, 12, 14, 16, 18 something. And for the face centered, it is 3, 4, 8, 11, 12 and something. This is the summation of this value. So out of this number of value, if your XRD data after indexing, if it is matched with 1, 2, 3, 4, out of this number of reflection, if it is matched with 5 to 6 reflection, then you may claim your material which is matched with this FCC or face centered cubic system. So these are the selection rule for the reflection in cubic crystal. See, these are the HKL planes which are reflected by the simple cubic, and this is the value of H square, K square and L square. So this is 1. So simple cubic, all are allowed it, but body centered, it is 1, that means it is odd number, it is not allowed it. But in FCC it is also again not allowed it, because in FCC we know the HKL value either may be odd, either may be even. So here 0 is considered to be even number for the case of HKL. So 1 is a odd number and 0 is a even number, so it is a mixture of odd and even. So that is why for the FCC it is, this reflection is not allowed it. So find one more example for the FCC. This is 3, 1, 1 plane. 3 is a odd number, 1 is a odd number, so it is allowed it. But for BCC it is not allowed it, because the value is 11, which is again odd number. But if it is 12, then it is allowed it for the BCC also, and this 2, 2, 2 is all are the even, so that is why it is again allowed it for FCC also. So this chart is very important for determine the allotted reflection planes in a cubic crystal system. So here is an example that I am going to discuss. Index the pattern and determine the HKL value. Also find the lattice parameter of given XRD pattern. So this type of XRD pattern is coming from the XRD machine, because they gives the data in the form of 2 theta versus intensity in the Excel sheet. So I draw this 2 theta and intensity in the Excel sheet. I got this type of graph. So this graph having, this is the intensity, maximum intensity here at the position of 2 theta, that is 38.43, and here is the one more 2 theta, that is 44.67, then 65.02, likewise 1, 2, 3, 4, 5, 6, 7, 8 reflection is there, and having all the reflections having the different theta value. So this is started with the 38.43 maximum theta value and ended with the 110.63 minimum theta value. Okay, so this is already given by the instrument. So what you have to find out, you have to find out by HKL planes of this reflection, these reflections on all the reflection, and also find the lattice parameter. So if you find the lattice parameter and HKL planes, then by using some calculation or some tricks, you can easily say your material either it is a face centered, body centered, or it is a simple cubic. Okay, so these are the some steps that I am going to apply to identify or indexing the XRD pattern. First, identify the peaks. Just you go here and you can identify these peaks. So here I identify the peaks. There are 8 number of peaks here. Determine the sin square theta value, then calculate the ratio of sin square theta by sin square theta minimum and multiply the appropriate integers. So select the result from third column, that I will discuss in the next slide, and then after compare the result with the HKL values and identify the sequence of 2, 4, identify the sequence, like here I am discuss this sequence, identify from the sequence, and you can say your material is either body centered or face centered or primitive. So this is the first step. Here I got this first step, this 38.43, 44.67, 65 point, this all angle 2 theta angle I plotted in this column, 38.43, 44.67. So these are the, for the 8 reflections or 8 peaks, these are the 2 theta values for the different peaks. Now for the next step, I divide this 2 theta by 2 such that I get the theta value, and I apply, and from this theta value I find the sin theta, and squaring this sin theta I will get the sin square theta value. So Here are the sine square theta value. So you can do this experiment, this calculation using the Excel sheet. Otherwise you can use the scientific calculator. Okay. So this is the second step that have been done here. Now the third step is to calculate the ratio of sine square theta and sine square theta minimum. So this value is the sine square theta minimum. So next in this step we're going to divide this sine square theta minimum by all these values. So first, if I divide this value by this 0.1083 divided by 0.1083, we'll get 1. Again 0.1444, it is divided by 0.108, we'll get 1.33. Again divide by this value by this theta minimum, we'll get this value. So likewise we do, and I find these values in this column. So next is to multiply these equations, this value with the integers. Why? I will tell you. This is multiplied by 1, and again I am doing sine square theta by sine square theta minimum, and again I multiplied by 2 here and I get these values, and I multiplied by 3 here, I get these values. So if I multiplied this sine square theta by sine square theta value by 2, I get the integer value, not in a fraction 200, but here I get the fractions 5.333, 7.333. Here I get the integer 8, whole number. So here 10.665. so it should not be in fraction, it should be in particular. Suppose it is 10.99, then you have to consider it is a 11. Okay, so that is why I'm going to this fraction to reduce the integers number. Okay, so that is why I'm going to multiply this by 1 first, then 2, then I'll multiply it by 3. So up to the multiplied by 3, the sine square theta by sine square theta minimum, I get this whole number is here. This is 15.998998. That means you can consider it is very nearer or close value to the 16. So you can put this value by 16. Here it is 18.998. So you can say it is a 19. Here it is a 19.997. So you can say it is a 20. Okay. But if it is a 13.331, so you cannot say it is a 14. Okay. If it is nearer to very nearer to the next number, then you can consider that is the next integer number. Number 3, that is why select the result for 3, that L h square k square plus L square as a series of integers. So this will be a series of integers. This 18 becomes 19, 15.99 becomes 16, and 19.99 becomes 20. So here I get compare the result with the sequence of h square, k square and L square value to identify the Bravais lattice. So this 3 becomes 3, 4 becomes 4, and just time changes 15.699 to 16, 19, and this is for 20. So this is actually the h square plus k square plus L square value. So this is the family of 1 1 1 for the HKL, because if I squaring 1 plus 1 square plus 1 square, then I got the 3. If I squaring 2003 family, for the h is equal to 2 square it is 4, plus 0 plus 0, so it is a 4. Now this is the family 8 means 220. How? Because this family belongs to h square plus k square plus L square is 2 square plus 2 square plus 0 is nothing but 8. So likewise you index all the values. For 3 means it is 1 1 1, and by applying this equation, sine square theta is equal to lambda square by 4a square multiplied by h square plus k square plus L square. Now you know the HKL value. Okay, these are the HKL value, and lambda is fixed 1.54 angstrom unit. Keep it in mind, because this source is for Cu. The target material here used for the XRD is copper, and copper gives the 1.54 angstrom unit. So put the value of lambda is 1.54 with the angstrom, which is always fixed, and put the value of h square plus k square plus l square, that means 1 1 1 here, and sine square theta, you know the sine square theta value, this is for the different HKL value, and put here is a 4 divided by 4 a square. So you have to calculate, if you know the sine square theta value, lambda value, HKL value, so you have to calculate by using this equation the value of a. So a means lattice parameter. So here it is clearly mentioned HKL values and the lattice parameter, such that I get the conclusion here. It is the conclusion. I find the HKL values, that is 1 1 2 0 0 2 2 0 3 1 1. Okay, and also if I averaging this all the a value, then I will get the average the lattice parameter, then I will get the lattice parameter is 4.0539 angstrom. Okay, so it is started with the point 111, that means it is started with 3. So let me show this slide. See, if it is a face centered, the first reflection will be 111, means h square plus k square plus l square is 3. So that means this cubic system is a FCC or face centered cubic system. That may be the one of the conclusion of this lecture. So this is the final conclusion, to find HKL value, which is this one, and this lattice parameter in this one, and it is the first reflection plane is 111, so that is why this is the face centered cubic. So this given XRD pattern is, this first reflection is 111, and so that this is the face centered cubic system. So likewise you will going to find out the indexing your HKL values, indexing the XRD data by finding the HKL values and the lattice parameter. So thank you for watching this lecture. I will give some example to solve you as a homework, and you will post me in the comment box also, or in the Google form also. Thank you for watching this lecture.